This is Eric, and today we're going to be talking about mean and variance. So, if you have a probability distribution function, it will tell you every possible outcome and the probability associated with that outcome. So, for example, here's one for the household income in the US in 1971. And it shows us that in 1971, about 1% of the people made $200,000 a year or more. So a probability distribution function is nice, especially if we can graph it. We can get some very interesting insights from it. However, occasionally we might want to summarize it in a shorter format than a big, huge list of numbers or a graph. And one of the ways we do that, the first thing we might want to do is calculate the expected value. The expected value is just essentially the average of a probability distribution. So imagine that you were going to reach into an urn, and in those urn there's little bingo balls, and 70% of those balls say $1 and 30% of those balls say $2. And the probability distribution would look like this. And if you wanted to calculate the expected value, which is what would happen if you played this, if you reached in and grabbed a bunch of balls and calculated your average, then 70% chance of $1 and a 30% chance of $2, you can see that you can't just add up those two numbers. Rather, you have to take a weighted average. So you would say 70% chance of 1, so that's 0.7 times $1, plus a 30% chance of 2, so that's 0.3 times $2, and that would give you an expected value of $1.30. So that's how you calculate the expected value. What you have to do is you have to take the value of the first outcome times the probability of that outcome plus the value of the second outcome times the probability of that outcome, and go all the way through it. So let's do another one. Let's do it for a fair six-sided die. So the probability distribution function of a fair six-sided die looks like what? Write that down. Okay, it looks like this. It's 1/6 chance of getting a 1, 1/6 chance of getting a 2, 1/6 chance of getting a 3, and so on. So if we want to calculate the expected value of a die, which is what the average would be if we rolled the die a bunch of times, then it's 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 all the way to 1/6 times 6. Then if you add all those things up, you end up with 3.5. So the average roll of a six-sided die is 3.5. Now notice, we call this expected value. We'll call it average. If you rolled it a bunch of times, that would be the average you would get. The expected value is the true long-term average based on the probability distribution function. But notice it's 3.5. So although we call it expected value, you would never expect to roll a 3.5. So it's the long-term average. All right, let me let you guys do one. So let's take the cheat die that we made up, where we took the 1 and we drew more dots onto it, so that a die now has no 1, but it has 2 5s. So there's a 2, a 3, a 4, 2 5s, and a 6. So first, write the probability distribution function of that die. Okay, it should look like this. 1/6 chance of 2, 1/6 chance of 3, 1/6 chance of 4, 2/6 or 1/3 chance of 5, and 1/6 chance of 6. Now, calculate the expected value. Remember, it's the value of the first outcome times the probability of getting that value. So you calculate it for this cheat die. So the average that you should have calculated should look like this. We take the first outcome, which is 2, and multiply it by its probability, which is 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 2/6, plus 6 times 1/6. And when we add all that together, we get 4 and 1/6, or in decimals, 4.16666666667. Okay, So that's how you calculate expected value. So what can we do with expected value? Well, you can look at it and say, seems how this is the long-term average. What is going to happen if we keep observing this or running this experiment or taking this gamble? And I'll give you an example from the lottery. So here's an example from the Texas Lottery. It's a game called Lucky 7, and you can go on the lottery website and download the probability of winning. So you can see the the PDF, the probability distribution function of this is displayed right here. So there's a 1 in 119,942.96 chance of winning $777. There's a 1 in 3,982.64 chance of winning $100, etc. So this ticket sells for $2, and if you go through, you can calculate the expected value of one of these lottery tickets by multiplying the outcome, the value of the outcome, times the probability of that outcome, and doing that for all the outcomes. And if you do that, what you find is that your lottery ticket's worth about 60 cents. So it costs $2 and it's worth 60 cents. And this is why statisticians don't like to play the lottery. Okay, so if you just learned one thing out of this class, don't play the lottery. And so we've made you money already. Okay, so that's the expected value, which is also called the mean, which is also called the average. And it's good for telling you what the middle is if you have a nice reasonable distribution. However, sometimes the middle, the central tendency isn't well reflected by the average. So for example, if you say, hey, what's the average income of a Rawls College of Business undergraduate, starting salary, then you might go and say, oh, look, it's, $300,000. And then you say, wow, that's really good. It's like, well, yeah, but that includes Patrick Mahomes' $100 million contract. So maybe if we threw him out, it would be closer to like $50,000. Okay, so the average doesn't necessarily represent the middle very well. Here's a good example. If we look at income distribution, then you can see in the United States, the mean income in 2015 was about $80,000. So this is household income. So the average household in the United States made about $80,000. But if you look at this picture, you can see there's a whole bunch of people who are making, a whole bunch of households, sorry, this is the whole house, so this is all wage earners in the house, who are making over $200,000. So there's about 3% of people making between $200,000 and $250,000, and there's about 3.5% making over $250,000 a year. And so that's skewing the mean a whole lot, because when we average across people, those people are are weighing heavily. I guess Patrick Mahomes is probably one of these people. And so instead, we might want to look at the median income. And the median income is where half the observations are above that number and half are below. So in terms of statistics, it would be where the CDF, the cumulative distribution function, equals 50%. So the probability of getting this number or less is 50, and the probability of getting this number or more is 50. In the United States, we look at that and we see that the median household income is $56,000. So that means half of households, this is the whole house, are making less than $56,000 a year. So it sounds really good to say that our average is 80, but when half the people are making less than 50, suddenly that doesn't seem so good. So if you have a skewed distribution, if you have a nice symmetrical distribution that looks the same on both sides, then your mean and your median are going to be close. But if you have a skewed distribution, then they may be far apart, and median might be a better representation of what's going on, as it is with income. There's also the mode, which the mode is the most common observation. For if you have a probability distribution function like this one, the mode is actually just where it's the tallest. So here it looks like it would be $20,000 to $24,000 or $25,000. So that's the most common amount of money that households report making. So the most common household income is 20 to 25. 50% of households make less than 56, and the average is 80. But that's because there's a lot of people on that far end, or there's not a lot of people on that far end, but the people on that far end make a lot of money. So these are the measures of central tendency, and sometimes we often report these. Hey, here's the average of something. It's better to look at the whole distribution function and draw it as a graph because it can tell you some different sorts of things. But it's also worthwhile to talk about the mean and the median and stuff because we're going to use those later for some more of our stuff that we look at. Now let's move on to talk about the variance. So to motivate this, let's pretend for a second that I were to tell you that the average height in the class, the MBA class, was 65 inches. And I was to tell you that the average starting salary was $65K. You might say, okay, that seems reasonable, that those are the averages for the MBA class. Now, what if I told you there was somebody in the MBA class who had a starting salary of $90,000 a year? Well, you might say, okay, that seems, that's good for them, but that doesn't seem, freakish or anything. It seems like that could happen. On the other hand, what if I told you there was somebody in the class who was 90 inches tall? Well, that's 7.5 feet tall. You might say, yeah, I don't think there's anyone that's ever graduated from the Rawls College of Business that's 7.5 feet tall. So the reason for this is that some things just are more spread out than other things. So if you look at these two graphs, for example, a graph of height and starting salary, you can see that starting salaries are just more spread out than heights. You can also see this if you think about weight. If I said the average height of a male in the Rawls College of Business is 6 feet tall, and the average weight is 200 pounds, you might say, okay, that's fine. And I say, but I know this guy who weighs 300 pounds. And you might say, that's a big person, but that doesn't sound weird to me, even though he's 50% heavier than the average person. But if I said, oh yeah, and I also know this other guy who's 9 feet tall, you would say, no, you don't, Eric. There's nobody that's 9 feet tall. Okay? Once again, it's because weights have more variance. They can spread out more than heights. Heights are much more fixed by our skeletal structure. Okay, and these can have a variety of meanings, but let's talk about how to calculate it. So what we want to do here is we basically want to say how far away are things from the average. So we calculate the average, the expected value, the mean, whatever you want to call it, but how far on average are things away from the average? So we say the average height is 65 inches, but how far are heights on average away from that? Or the average income is 65K, but how far on average are things away from that? So the way we want to calculate that is we actually take the squared distance. So what I want to do is calculate the average, 65, and then I would say, Eric, say 68 inches tall. So you're plus 3. But if I were 62 inches tall, I would be 62 inches tall, then I would be minus 3. And when I added those up, they would cancel out. On the other hand, if I square them, then I could say plus 3 squared is 9, and minus 3 squared is also 9. So those two distances are now the same. So what we do is we say how far away is each observation from the mean, and then we square that distance, and then we take the probability of them being at that outcome. Okay, let's do a six-sided die again. So what we want to do is first calculate the mean, or the expected value, and then we want to look at every possible outcome and see how far away that outcome is from the expected value, and square that number. Then multiply that squared number times the probability of being there. So for the expected value, we already know is 3.5. So for a 1, we take 1 minus 3.5, which gives us negative 2.5. Then we square that, which gives us 6.25. and that's the squared distance, then we have to multiply that by the probability of getting a 1, which is 1/6. We do that again for 2, so that's 2 minus 3.5, which gives us a 1.5. We square that, it gives us a 2.25, and then we multiply that by the probability of getting a 2, which is 1/6, and we get 6.75. And when we add all these things together, we end up with 2.916. Okay? So the variance of a six-sided die is 2.91666666666. Okay? So that tells us a measure of dispersion of a roll of a six-sided die. All right. Let you guys do it with the cheat die that has 2 5s and no 1. So calculate the variance. Again, this is it's the squared distance from the mean times the probability of each of those outcomes. So let me give you a second to calculate the variance of the cheat die that has 2 5s and no 1. Okay, so when we do that for the cheat die, the expected value is 4.166666. So the first value that we can get on the die is a 2. So if we take 2 minus 4.166666, we get minus 2.166666. When we square that, we get 4.6944444. Then we have to multiply it by the probability of getting a 2, which is 1/6. We do the same thing for 3. We do the same thing for 4. We do the same thing for 5. I'll go through 5 real quick because it has a different probability. So 5 minus 4.166666 is 0.833333. If we square that, we get 0.6944444, and then we multiply that by 2/6. It gives us 0.231 whatever. And we add all those up, we get 1.805. So the variance of the cheat die is 1.805. Okay, so that means that the cheat die is a little bit less variable than the regular die, which makes sense because we've taken one of the extreme values and moved that closer to one of the middle values. So it makes sort of sense. So this is variance. This is an important statistic. The problem with variance is that because we've squared everything, the units are squared. So if we're talking about height, we have square inches, which kind of makes sense. But if we're talking about income, we have square dollars, which kind of sounds like something from the 1920s political campaign. So that doesn't make any sense. So typically what we do is we'll take the square root of the variance, and that's called the standard deviation. The variance is denoted as sigma squared, and the standard deviation is denoted as sigma. Sigma, the Greek letter for S, for standard deviation. And the mean is denoted as mu, which is the Greek letter for M, for mean. In any case, the standard deviation is in the original units, and it makes a little bit more sense. So we often report, here's the mean and here's the standard deviation. The mean and standard deviation of height in the United States, the mean is 70 inches for males, and the standard deviation is 3 inches, which means that the average squared distance is 9 between different men from the height of 70 inches. Let's review. We have the expected value, which is a weighted average of the outcome. Specifically, it's the probability of getting an outcome times the value if you get that outcome, summed up over all the outcomes. We have the variance, which is the probability of an outcome times the distance that outcome is from the average outcome squared. We have standard deviation, all those added up over all the possible outcomes. We have standard deviation, which is the variance, the square root of the variance. We can also use median, which is the middle point where 50% of the data is above that and 50% below, and the mode, which is the most common outcome. We're going to use these later, but it's worthwhile to keep track of them for now. Thank you, and see you next time.